Hi everyone, welcome back to my tutorials. To start off, we're going to be continuing back from the breadth first search traversal, which we finished. Now we're going to be covering the depth first search traversal, which is implemented with a stacked data structure, and well, it's a whole lot easier than breadth first search. Okay, to start off, 0 is the first vertex, the source vertex that we're going to be taking as usual. You can take any vertex actually, it does not matter. The order will be different, but well, the answer will still be correct. Now, since we always do it alphabetically, chronologically, and number-wise, serially, so let's do it with 0. So now this time, well, we start from the 0 and then we work our way through, and this time notice that this graph is different from the last one, as it has arrows pointing to which vertex to go to, like it's a directed graph. But well, it can be done in both directed and undirected graph, but for explaining properly, I'm using directed graph because I'm later on going to be explaining the finishing time and starting time thing, which can be properly explained with the directed graph. It can also be done with the undirected graph, but well, it's easier to explain with this. So well, now we go to the first vertex that it's pointing to, which is 1. We can go to 2 also, but then like I said, serial by we go to. So well, we mark 1 as visited, and then we add it to the stack. This time we add it to the stack, and notice that the shape of the shape this time is a little bit like a stack, because as I said, it's not Q. We don't do it horizontally, we rather do it vertically. So we write down the write down the number 1 and we push it into the stack, and then well, we then from 1 we're gonna be, it's not like we're gonna be going, well, we're gonna be using this and going adjacent to it again like BFS. We're gonna continue from 1 and going to the next node, which is 2. So we push 2 into the stack, and then we mark it as visited. Still not getting the hang of this, sorry about that. Okay, so we push 2 into the stack, and 2 is the next node that we're gonna use as the source. Okay, so then we push 2 into the stack. Now we go to the next one, which is 3. So 3 is the next node that we're gonna visit. So we visit 3, mark it as visited, and then we push 3 into the stack. Okay, now again, this is kind of easy, right guys? So oh wait, we didn't mark 0 as the visitor. Well, it's the same thing, we started from 0 anyway. So 4 is the next node that we're gonna visit. So again, we push 4 into the stack, mark it as visited, and go to the next node, which is 6. See, it's following the trail, it's following the arrows, just like that. Then after that, how are we going to visit 5 and 7? Well, this is the only difference between BFS and DFS. It just traces back like a maze. Anyway, let's just first get over with this one. 6, mark it as visited, and then push 6 into the stack. Okay, now since we have visited all of it, like 0, 1, 2, 3, 4, 5, 3, 4, 6, now what's left is 5 and 7. So what we do is we pop off the items that we have on the stack. We pop it off, and then now we try to trace back. From there. Now 6 does not have any way to go through because 3 is already visited. Now we go to 4. So we pop off 4. 4 also has nowhere to go to. 6 is already visited, and 3 there is no arrow pointing towards 3. So we pop off 4 as well. Now we go to 3, we pop off 3, and then we try to look if there is any adjacent that's not visited. So which is what? 4, 6, 2. Well, everything is visited. So we pop off 3 as well, like we did. Now we go and pop off 2. Now when we are at 2 right now, we have 5 that's unvisited. So now we push 5 into the stack. So we mark it as visited, and push 5 into the stack. Okay, now after that, okay, let me just mark 1 as visited as well, because it looks weird when everything is visited and stuff. Okay, everything is visited, like only 7 is left. Now after that, we go and pop the one that's on the top, which is 5. So we pop off 5 from the stack, pop it off, see what's adjacent to it. We find 7 is adjacent to it, so we push it into the stack. 7 is now visited, so we mark it as visited. And well, now everything is visited, as we can see from the graph. Now let's just check, because we have to see the whole stack has to be empty. Now again, the only thing that's left in the stack is 1, so we pop 1 off and see if there's any unvisited stuff here. Well, 2 is visited, 0 is visited, everything is visited, it can't go anywhere. So well, oh sorry, you're not supposed to pop 1 off, you're supposed to pop 7 off. So we pop 7, which is at the top, and then see if there's anything adjacent to it that's unvisited. And well, there's nothing unvisited, so we now pop off the last element, which is 1, and well, everything adjacent to 1 is already visited. So this is the result. So we write down the whole result serially: 1 2 3 4 6 5 and 7. So this is the result. I should have written it before, but well, this is the correct answer. And well, if you do it this way, you can get, if you don't maintain the result as as soon as you start pushing items in the stack, it's fine. You can just write down the way it's written from bottom to top. Okay, so this is the final result. Now let's compute the finishing time. Now what's the starting time and finishing time? It comes adjacent to, like, it's used for like finding out the topological sort, which will come later on as well. Let's show for this example, S is the source vertex. Now 1 is the starting time, and then it goes towards A or C. So A comes first, so we go to A, and then we give 2 as another starting time. We go at like 1 2 3 4 5 6 7, like we just increase the count by 1. And then we go to B, 3, and then since there is nothing adjacent to B that is unvisited, since S is already visited, and S, the only out degree arrow from B is S, and it's already visited, we don't like we don't go towards it, and like we don't compute the starting time that time. So we start computing the finishing time now, which comes beside 3. So 4 is the finishing time. We go back, we just increase the count and go back to backtrack the arrows, and this time, so we just go towards, we don't go towards 2. Now look at this, we don't go towards 2 and write, we don't go here and write 5 here, because A points towards C and A has 1. If we go here, then this graph will just be finished here, 4 5 and 6. So, and then this whole graph will be left untouched, and we don't want that. So we have to compute the finishing time of all the vertices. So we go here, we go to 5, and then well, 5 has no out degree arrows, so we just compute the next finishing time, which will be here, which will be 6. Yeah, and then now we go towards 2, and then the next finishing time will be, the finishing time is always on the right side and the starting time is always on the left side. So the finishing time will be 7, and then here this time again notice S has another out degree arrow pointing towards D, and if we write 8 here beside 1, then this whole graph will be untouched again. So this time 8 will be the starting time for D. So 8, and then after that, when the next vertex that D points to is E, so 9 will be the starting time here, and then after that 10 will be the finishing time beside E, and then after that D D here will be 11 will be the finishing time here, because no out degree arrow points towards F. It's an in degree arrow. What's an in degree and out degree? In degree is the arrow that points towards a vertex, and out degree is the arrow that points outwards, away from the vertex. Anyway, so 11, and then now 12 here will be the finishing time. Now these two nodes still remain untouched. So we just start another starting time from here. So 13 will be continued, and then 14 here, 15 here, and then 16 here. So the starting time is starting time and the finishing time is computed properly, and well, that's the answer. Now if we want to do that same thing for our graph, well, we just compute from 0. So 1, then 2, then 3, then 4, 5, 6, 7, 8, 9. Now notice we don't write 10 here, because if we write 10 here, these two nodes will be lost. So 10, 11. Now we can write the finishing time from here: 12, 13, 14, 15, and 16. So the starting time and the finishing time are properly computed, and well, that's the answer. If you have any questions, please comment below. I'll be answering all your questions. And well, if you have any more confusion about starting time and finishing time, no problem, we will discuss it later on again for topological sorting, because that's where the main use of starting point and finishing point comes into, and also for strongly connected components. Okay, so let's just go look at this slide again. This is the algorithm. So this is, first we initialize all the vertices. White means again unvisited, and prev means the predecessor, which is null at the beginning. Everything is first initialized, and then for each vertex u, we just visit the vertex, and then we see time is the starting time, time equals to time plus 1, du is the starting time, and fu is the finishing time. So fu equals to time. This is how we trace back, and this is the whole algorithm. Now if you want to detect a cycle, then what we do is, here, like when we're doing in this loop, if color v equals white, that time when we visit the adjacent vertex, that time if the color v is not white, if it's gray or black, means if it's visited, that means it's a cycle. Like for example, like when we are going to 0, 1, and 2, and then when the arrow adjacent to, not for this one actually, because this is a cycle. So well, when we are going to 4, 3, 4, and 6, and then this arrow points, and then when the vertex adjacent to 6 is black, I mean for the algorithm, when it is black or gray, when it's not white, that means it's visited. If it's visited, that means it will form a cycle. So 3, 4, and 6 would form a cycle. So that's how you detect a cycle. So 3, 4, and 6, if there was a node adjacent to it, like if there was a node adjacent to it like this, suppose 8. Sorry about that. Let me just decrease the brush size. If there was a node adjacent to it, suppose it was 8, then, and it's not visited, I mean it's white color. So if it's like that, then it's not a cycle. But if it goes here and checks that this is already visited, that means it will form a cycle. So that's how you detect a cycle from the algorithm. Okay, so that's all about depth first search traversal. I hope you understood everything, and if you have any confusion, please just write down in the comments below. And well, don't forget to subscribe, and well, good luck.